Everyone's in love with the Agilent signal generator. Look, just because it's got a. We used to have those on the bench, by the way. They're in storage at the moment, but they're really, really good signal generators. But it just adds a nice touch of realism. There's an oscilloscope on there that looks like an oscilloscope as well, which is pretty good. So, have you got a PCB? Can you show us your PCB?
Oh,
the printed circuit board. Can you show us that?
No, I haven't.
Oh, okay. Fine. I'll come back when you have then. Good.
So L in this case is 4 millihenry.
Oh, things are getting technical over here. Look, we're talking about coils and millihenries and
Find out what that frequency is going to be.
1/2 pi root LCs. Look, it's all happening here.
I was just trying to explain this. All you've got to do is get it started. You don't need an AC signal to drive that. You just got to get it started.
That's right.
And so trying to explain that we need to calculate what you think your output would be before we simulate that, so we know what we're looking for.
So you've got your resonant coil there, or your tank coil. That's right. So you just got to get the values in there from 1/2 pi root LC. You know what the value of the capacitor is because it's fixed inside the kit, right? The only thing you don't know is the size of the inductor. And that's what you've got to work out. Because so you measure the frequency at which it resonates. You can measure that, can't you, on the oscilloscope? And then once you've measured that, of course, you can calculate how big the inductor is.
You said we can measure the what?
You measure the frequency. The gentleman, where is he? He's still in the lab, isn't he? He's winding a coil, and what that coil will do is, so you take your metal detector and you press the button and you connect it to the signal generator, you can actually see what frequency the metal detector is vibrating at. You can measure it on the scope. Well, once you know the frequency it's vibrating at, you know what size the capacitor is, so therefore you can calculate what size the inductor is. I was going to say it's as simple as that, but it's not quite as simple.
He's still looking at this thinking, I don't want to do maths. I didn't come here to do maths.
Maths is good. Maths is good. It gives you the whole understanding of things, doesn't it? What do you say?
Yeah, of course.
Maths is good when it works and when you see in reality that the maths are telling you the truth.
Output frequency. So,
Mike's found an online one to take the complexity.
feeling a bit happier now, don't you? So here we have 1 microfarad. So we have here, but this is in picofarad at the moment. So if I was to change that to what you've got here with microfarad, and I put in there your value there of 1. Yes. And then your inductance here, you've got 1 millihenry, which is not small at all, is it, John?
Millihenry, no, it's quite big.
Then we'll put 1 millihenry
like
in
it's tiny,
here.
but it's actually very big.
Yes, and then you are expecting to see, if you built that circuit, we would see 5 kilohertz coming out of it.
No, definitely that metal detector is a lot faster than that.
A lot faster than
200 or something, isn't it?
So from the point of view of the metal detector, you had a 1.2 nanofarad capacitor, wasn't it? If I remember, I can't remember from the circuit.
3.3.
3.3, there was a selection that you could make, wasn't it? So
That's right, 2.2 and 3.3 it was, right?
nanofarads in there, yeah? And so if we had a 1 millihenry, we would expect a 2.77 kilohertz. So now if I change that, so we made it 1 nanohenry, yeah?
That's tiny.
And then we will actually make that 1 rather than 1 million. See, now we're going to get 2.7 megs out of it. You see?